Hello and welcome to this presentation. This is a presentation of a research work done by H.O. Onyishi and I.O. Jacobs entitled Investigation of the Relationship Between Processing Conditions and Creep Behavior of Plastics, a case study of PET. This presentation is for the 2020 Sustainable Engineering and Industrial Technology Conference. Let us start by looking at a typical aerosol container. As you can see in this slide, most aerosol containers are metals or glasses, which do not creep at room temperature. This is because the aerosol is stored at high pressure. So plastics are not good aerosol containers at the moment because they creep at room temperature. So this work studies the creep behavior of plastic as a function of their processing condition. Background of study. As stated in the previous slides, the background to this study comes from the fact that plastics creep at room temperature, unlike metals and glasses. So because of this, plastics are not good where high pressure is concerned. So for that reason, we look at the behavior of creep behavior of plastic as a function of the processing condition. So we are using PET, which is polyethylene terephthalate, one of the commonest plastics in the industry today, as our case study. Before we continue, let us look at typical plastic creep curves. So the curves shown in this slide are for polycarbonate measured at 23 degrees Celsius, that is room temperature, and a constant stress of 64 megapascals. So the creep curves are two types, the strain versus time and the strain rate versus strain. So for each of them, you have different stages of creep, the stage 1, stage 2, stage 3, 4, and 5. At stage 1, the strain is increasing with time on the strain time graph, and at stage 2, the strain is fairly constant with time. At stage 3, it is beginning to increase with time, and then at stage 4, it increases very rapidly, just like in stage 1 with time. And at stage 5, it is fairly constant again. So the aim of this is to try to observe the stage at which the material fails. And before we go on, it is important to define what creep means. It is the continuous deformation of a material under constant stress. So you keep the stress constant and see what happens to the strain. The problem statement is just a restatement of the background to the study. Plastics are not used in high pressure applications like the aerosols. So we are looking at solving that problem by looking at processing conditions of plastic that bring them closer to being applied in high pressure applications. The aim of this work is to investigate the creep properties of polyethylene terephthalate (PET) as a function of the processing conditions. To do that, we prepare the PET testing samples, we process them, and we keep a control sample, which is the unprocessed sample, and then we carry out uniaxial and biaxial creep tests on all the samples, and we analyze these results. The significance of this work is the fact that it bridges the gap between simulations and actual experiments, because a lot of work done on plastics today are done by simulations due to the high cost of experiments and the time factor as well. The scope, of course, is PET. The plastic used for the experiment is PET. Coming to methodology, the material for this work was a freshly made PET sample. So the PET sample was cut into square plates. So processed samples were produced from these square plates by biaxially stretching them. So two different stretch ratios were used, the 2 by 2 and the 3 by 3. So 2 by 2 means the sample was stretched twice on each side, and the same way for 3 by 3, 3 times on each side. So that gave us three different samples, the original or unprocessed sample, the 2 by 2 sample, and the 3 by 3 sample. Then creep tests were carried out on all these samples, and that is uniaxial creep tests, And the uniaxial creep test were three types for three different constant stresses. So you have the 32.8 megapascal constant stress, the 39 megapascal constant stress, and the 45 megapascal constant stress on each of the different samples. Then after this, a biaxial creep test was done on a PET bottle. So biaxial in the sense that the test was done for both the hoop direction and the axial direction. So this will be explained later as we go on. So this slide gives the details of the biaxial stretching. So the sample was heated to a temperature higher than the glass transition temperature to soften it, and then the biaxial stretching machine stretched it to the specified stretch rate. Okay, this slide further illustrates the biaxial stretching of the sample. So the first picture shows an unprocessed sample side by side with a processed sample. The second picture shows the clamps of the biaxial stretching machine. So to process the sample, you clamp the sample in the clamps of the machine and set the machine to heat it to a temperature higher than the glass transition temperature. Then the machine will stretch it to a preset stretch ratio. So because of the heating, the clamps are able to dig into the sample so that during the stretching, it doesn't lose the grip. Okay, this slide has two videos. The first one shows how the clamps are adjusted so that the clamps fit the size of the sample. So after adjusting them, you make sure each of the clamps has a hold on the sample. So as you can see, each clamp is connected to a metallic hose that carries air. So it uses a pneumatic clamping system. So it will force the clamps to hold the material by forcing through air pressure. So the second video shows the stretching process.
3, 2, 1. Beautiful.
So from this video, you can see that the heating element on top of the sample shifts away from the sample so that there is no further heating during the stretching. So after this, you now unclamp it by pressing a button that will release the clamps before you remove the material. Okay, this slide illustrates what I've said before, the different uniaxial creep tests that were carried out for each of the three samples. This slide shows the uniaxial creep tester with the dumbbell sample clamped between the two clamps. So this machine will apply a constant stress on the sample according to your settings, and it will measure the strain for the duration of the test. Now the biaxial creep test. So this creep test was done on a PET bottle, as you can see in the pictures. The PET bottle is first of all painted in such a way that changes in the shape can be picked up by the cameras, as you can see. So these cameras, the images picked up by these cameras will now be analyzed by a software called DIC, Digital Image Correlation, which translates the changes in the shape of a material into strains. So this was one way of measuring the strains. The other way is by strapping strain gauges on the bottle in either direction, the hoop and the other directions, so that the strain gauges can measure the strains in real time using a lab view interface. So the internal pressure is provided by means of a hose connected to an air cylinder on the outside. And you see that the whole system is covered so that there are no optical interactions from the outside with regard to the DIC. So we see the results for this in a subsequent slide. Let us now look at the results and discussions. The first one we are looking at is the uniaxial creep test at 32.8 megapascal constant stress. So as you can see, the original sample creeps the most after a few days, approaching the secondary creep if you compare to the typical creep curve that we showed at the beginning, while the 2 by 2 and 3 by 3 samples we are still at the primary creep. And this is also shown by the strain rate versus strain graph. This is the uniaxial creep test at 39.0 megapascals. So the original sample lasted only few minutes, so to say, and it failed, while the other samples lasted a couple of days, a number of days. For instance, the 2 by 2 sample failed after 2 days, and the 3 by 3 sample stayed for more than 3 days. So you could see that the higher the stretch ratio, the more the resistance to creep. The same trend is observed for the 45 megapascals constant stress uniaxial creep test. You notice that the original sample lasted only few seconds, while the 2 by 2 sample approached the tertiary creep stage after more than 10,000 seconds. But it didn't last up to a day. A day would be around 86,400 seconds. Now, the 3 by 3 sample lasted for more than 2 days for the same 45 megapascals constant stretch, showing that the higher the stretch ratio, the more resistance to creep. Okay, this slide shows the strain rate versus strain for the 3 samples at 45 megapascals. The original sample clearly has entered the secondary, has reached the end of the secondary creep stage before failing, while the 2 by 2 and 3 by 3 samples all failed at the secondary creep stage if you compare to our original typical creep curves for plastics shown at the beginning. Finally, on results and discussions, this slide shows the results from a biaxial creep test on a PET bottle subjected to a 4-bar internal pressure. The result shows that the axial strain is about half the hoop strain, which is in general agreement with literature. So this is the result gotten from the strain gauges that measure the strain in real time. The DIC measurements did not produce comprehensive results, so they will be looked into in further researches. In conclusion, this has been a presentation of a research work that investigated the creep behavior of PET as a function of the processing conditions. The first conclusion here is that plastics indeed creep at room temperature under constant stress. Note that the governing processing condition used for this work was the stretch ratio. Every other thing was kept constant, like the processing temperature, the strain rate, and the mode of deformation. So it was observed that the higher the stretch ratio, the higher the resistance to creep for uniaxial creep tests. The other test done was the biaxial creep test on a PET bottle, and it was observed that the PET bottle creeped at room temperature in both the axial and the hoop directions. Furthermore, it was observed that the hoop strain was twice the axial strain throughout the duration of the experiment. This largely agreed with literature. Finally, further researches are recommended. This can be done by varying the processing temperatures, the strain rates, and the modes of deformation. Moreover, the biaxial creep test can be further explored by having different PET bottles with different processing conditions and comparing their biaxial creep test results. Thank you for watching this presentation. If you have any questions, please send them to my email address or mobile number. Both of them are shown on the screen. Thank you. The next slide shows the references.